Hello everybody, my name is Mashinchi from Caltech University. I would like to present our paper entitled A New Transformer-less Single-Switch Boost DC-DC Converter with Lower Stress. My presentation includes a short introduction about boost DC-DC converters, and after that the topology of the proposed converter will be introduced, and operating principle of the converter will be explained. And then comparison analysis and simulation results will be explained. And finally, we have conclusion. Boost DC-DC converters are widely used in a large number of power conservation applications, such as photovoltaic systems, electric vehicles, and power factor correction, and so on. These converters are categorized to non-isolated type and isolated type. The isolated type are suitable for high power levels, and this type of DC-DC converters meet most utility grid standards, but they need precise for coupled magnetic design for high voltage gains. Non-isolated DC-DC converters often have a simple structure with low weight and also cost, and they are suitable for low to medium power levels. The techniques that used to increase the voltage gain in this type of converters is couple inductor technique, and also switch capacitor techniques and voltage lift techniques. Here we have the topology of the proposed converter, include one power switch and one inductor with 4 capacitor. For analysis of the converter, assumptions are that the capacitors are enough large and the voltage of these capacitors considered constant, and also EMI is neglected, and proposed converter is analyzed in steady state. The converter is analyzed in turn-on state of switch and turn-off state of switch. In turn-on state, inductor L1 and capacitor C2 are charged, and capacitors C1, C3, and C4 are discharged. In turn-off state, the inductor L1 are discharged, and C2 also are discharged, and C1, C3, and C4 are charged. C4 provide the energy of load at turn-on state alone, but in turn-off state along with inductor L1 and capacitor C2. The voltage gain and also stress of the switch can be obtained by these equations. As can be seen, the stress voltage of the switch is half of the voltage output voltage range. Comparison between the proposed capacitor with other literature shows that the voltage gain of the proposed converter is very close to the other ones, but also the switch stress of the proposed converter is lower than the others. Here we have simulation results for given values of duty cycle, input voltage, and other components. As can be seen, the inductor is charged for on state of switch and discharged for off state of switch. The maximum value of the voltage across the switch is half of the output voltage. We have conclusions. A new structure for non-isolated boost DC-DC converter was proposed with a lower stress of component, and also the voltage gain and switch stress of the proposed converter has been calculated and compared with other structure. The comparison result shows that the proposed converter has an acceptable voltage gain with low stress voltage of switch. The output voltage was increased to 48 volts by considering duty cycle equal 0.5 for input voltage of 12 volts in CCM operation mode. This converter is applicable in low power applications. Thank you for your attention.